In this video, we're going to learn about how to deal with a diagonal force in a force problem. So what we're going to do to learn about forces is we are going to use what we call a force table. This is a device that I have at work that we use to apply forces in different directions. So what we do is we hang weights on these strings that go over pulleys, and this is a shot from a top view. And what we're going to do is I'll have a free body diagram here to show the forces in different directions. So right now I have a 5 Newton force up, a 7 Newton force to the right, 7 Newton force down, and a 7 Newton force to the left. So we can see that this is unbalanced, and so this object, it's applying the force on this ring here. And so we can see what happens, so you can get an idea of what does the force table do when the net force is unbalanced. So we're going to move forward, and you can see that the ring moves upwards, right? That's what we would expect to happen. So now that you know what it looks like, let's take a look at some other situations when the forces are unbalanced in two directions. So here we have 5 newtons up, 5 newtons to the left, and 7 down and to the right. So it's unbalanced in two directions. Let's see what it looks like on the force table when this is the case. You can see that it moves off in a diagonal direction, which is what we would expect. Okay, and now we want to look and see what does it look like on a force table when there is no net force. So in this case, there are equal forces in all directions, no net force, and so if I let go, you'll see that the ring stays still. Now that we know how the force table works, let's actually look at a situation with a diagonal force. So what we're going to do is we're going to have two forces. We have two pulleys, one down and one to the left, and they're both pulling with 7 newtons of force. And then we have another one that's at a specific angle, specifically 45 degrees from the horizontal. Okay, and so this force is an unknown force, and the question is what type of force, or how much force do we need at this angle in order to balance these two forces? So you can think of it like before we had a four-way tug of war, someone pulling up, down, left, right, and now we have a three-person tug of war, someone pulling down and to the left, and then now we have one person that has to do the job of two. He's got to counteract the force pulling up, which should have been 7, and he's got to take the place of the force pulling to the right, which also should have been 7. So the question is what should the amount of this diagonal force be such that he can do the job of the person pulling right and up and still have this be balanced? Now I want you to pause the video and take a guess of what you think it should be, and then we're going to test certain different student ideas. So write down a couple of guesses if you think, and then when you're ready, proceed and we'll see what happens. All right, so here is a common student example. Some students say, you know what, I think that it should be, this diagonal force should be 7, and that should balance. So 7, 7, and the diagonal should be 7. Let's see what happens when this is the case. So we can see that the force, 7 newtons diagonally, is insufficiently strong. The person pulling diagonal is not strong enough to counteract for both of these two forces. Let's try another idea. All right, another common example that students come up with is they say, well, you know, there was 7 down and 7 over, and this guy has to pull up by 7 and over by 7, so therefore, let's just add the two forces together for a total of 14. If we do this, let's see what happens. And you can see that 14 is just too much force. It pulls off into this direction. Let's try another student idea. So this is one more idea that students often come up with after we try our last two examples. Once we try with 14, which is too much, and 7, which is too little, a lot of times students will say, well, what if we just average the two? One was too much, one was too little, so just average the two. That average would be 10.5. So if we have this pulling at 10.5, let's see if that is sufficient to act as 7 up and 7 over. And you can see in the end, it's actually just a hair too much. So the real question is now, what can we do in order to figure out the amount of force diagonal that will act as a force over of 7 and a force up of 7? Let's take a look. All right, so again, we want something to act as 7 to the right and 7 up. Well, why don't we just add these two like we did the first time? But this time, these are vectors, right? Let's add them like vectors. How do we add vectors? We add them head to tail. So if we draw these vectors head to tail and then draw the resulting vector, okay, the diagonal one, and we might say, okay, well, what force pulls over, goes over this much with 7, and goes up this much with 7. And we can do some math and figure that out. How do we do that? A squared plus b squared equals c squared, right? So a squared, 7 squared, plus b squared, 7 squared, and square root that should give us our answer, 9.9 newtons. Let's check and see if it works. And sure enough, this is finally the amount of force needed so that it acts as 7 over and 7 up. So, what is the point of this? You need to know that when you're dealing with forces, you can add up forces, or, and we're going to learn how to do this, even split up forces that are diagonal into components, right? You can look at forces as really a combination of multiple forces, 1 over, 1 up, or you can combine something over and up into a single force that's diagonal. And when we add those forces, we always do it with vector math because forces are vectors.